Welcome to The Explainer. Today, we are diving into the world of incredibly precise, super cold chemistry that makes sure the medicine you take is not only safe, but actually works. You ever just look at a pill and wonder, how in the world do they know exactly how much of the active ingredient is packed inside? It's a really important question of quality control. And the answer, well, it lies in some pretty fascinating chemistry. So let's explore this idea by looking at a very specific challenge, what I'm calling the sulfa drug puzzle. Now, sulfa drugs were some of the very first miracle antibiotics, and being able to measure them with pinpoint accuracy is still a huge deal today. So what makes these drugs so special? Well, it's their chemical fingerprint. Almost all of them share this key component called a primary aromatic amine. The easiest way to think about it is like a special chemical handle, something we can grab onto. And getting that measurement exactly right is absolutely critical. If there are too few of these molecules, the drug just won't work. But if there are too many, it could actually be harmful. So we need a totally reliable way to get an exact count. So how do we solve this puzzle? How do we count those molecules? Well, the solution is this really elegant technique with a very specific name, and it's a true cornerstone of pharmaceutical analysis. It's called diazotization titration. Okay, I know that sounds super complex, but the idea behind it is actually pretty simple. It's a process that systematically finds every single one of those primary aromatic amine molecules and changes it into something else we can easily track, a diazonium salt. So here's the basic idea. You take your drug molecule, you add a few key chemical ingredients, and you essentially put a chemical tag on it, turning it into that diazonium salt. By measuring how much of our chemical it takes to tag all the molecules, we know exactly how many were there in the first place. Simple as that. But like any good recipe, the success of this whole thing depends entirely on using the right ingredients under exactly the right conditions. So let's take a look at what actually goes into the beaker. All right, here are our main players. You've got the drug itself, of course. Then you have sodium nitrite and a strong acid. Now what's cool is that the sodium nitrite and the acid actually react with each other first to create the real active ingredient, which is nitrous acid. That's the chemical that does the tagging. The potassium bromide? Oh, that's just a catalyst, a little helper to make the whole reaction go faster. Okay, so you can have all the right ingredients perfectly measured out, but if you miss this next condition, the entire experiment is a complete failure. It is absolutely 100% non-negotiable. The entire reaction has to happen in an ice bath. We are talking between 0 and 5 degrees Celsius. That is barely above freezing. So why on earth does it need to be so incredibly cold? It's because that diazonium salt, the tagged molecule we're trying to count, is unbelievably unstable. If things get even a little bit warm, it just falls apart. It releases nitrogen gas that literally bubbles away into the air. And just like that, your count is wrong, and the entire analysis is ruined. The cold is the only thing that keeps it stable long enough for us to get a good measurement. Okay, so we're slowly adding our reagent, we're tagging the drug molecules, it's all happening in a freezing ice bath, but how do we know when we're done? How do you see the exact moment you've tagged the very last molecule? Well, the answer isn't something you see in the beaker itself. Instead, chemists use this really simple but incredibly effective tool, a small strip of something called starch iodide paper. And here is the key to the whole thing. As long as there are drug molecules left to react with, all the nitrous acid we add gets used up instantly. But the very first drop you add after that last drug molecule is tagged, well, now there's leftover excess nitrous acid. And that's what triggers our signal. And this right here is the aha moment. Throughout the whole process, you take a tiny little drop from your beaker and you touch it to the paper. Nothing. White, white, white. But the moment you reach that end point, that one drop with the excess nitrous acid instantly turns the paper a deep blue. That's your signal. Stop. You're done counting. So, we've just walked through this cold, careful chemical dance. But how does it all fit into the bigger picture of medicine and science? Let's take a step back and see why this classic technique still really matters. Well, for one, it has some major strengths. It is incredibly selective. It only grabs onto that specific chemical handle, ignoring pretty much everything else in the mixture. It's also really sensitive and gives you repeatable, trustworthy results. That's why it's a foundational technique taught to every single pharmaceutical chemist. But hey, it's not perfect. It's definitely slower than some of the more modern methods out there. That strict temperature control is, frankly, a real pain. Sometimes that blue color can be pretty faint or fade quickly, making it tricky to spot the endpoint. And of course, it only works for that specific class of drugs with the right chemical handle. And its importance goes way beyond the textbook. This very technique is used to test the purity of essential sulfa antibiotics, local anesthetics like what your dentist uses, and even really crucial biological compounds like dopamine. So ultimately, that's the real takeaway here. Behind that simple pill in your medicine cabinet is this whole world of precise, demanding chemistry. And techniques like diazotization titration are like the invisible guardians, making sure that what's on the label is actually what's in the pill. Kind of makes you think, doesn't it? From the food we eat to the water we drink, what other invisible chemistry is quietly working behind the scenes to keep our world running safely? We'll see you next time on The Explainer.